Some of our strongest modern buildings are weaker than stone laid centuries ago. This is the forgotten science of stone materials, a field of knowledge mastered by ancient and medieval builders to create substances that outlast our own. By the end of this journey, you will understand how lost recipes and a different philosophy of building could hold the key to a more sustainable future. How did Roman harbors grow stronger underwater for 2,000 years? What secret made the stones of Gothic cathedrals so resistant to decay? We are going to uncover the hidden chemistry and intuitive genius that gave these materials legendary durability. This exploration does more than solve historical puzzles. It challenges everything we assume about progress and innovation. What does it say about our civilization when the old stones still have the most to teach us? These master builders operated within a world profoundly different from our own. For them, every stone, every handful of lime, every bucket of water held a specific essence. The world was composed of fundamental qualities like heat and cold, moisture and dryness, and the art of building was about balancing these forces within a material. This wasn't superstition, it was a practical framework for understanding nature's behavior long before modern chemistry gave us the periodic table. A limestone that felt cool and dense to the touch was understood to have different properties than a porous, warm sandstone. This intuitive system, rooted in the ancient knowledge of alchemy and natural philosophy, guided every decision. It told them which local quarry produced stone that resisted frost, which sands created a better bond, and how to mix mortars that would mature in harmony with the seasons. Their laboratory was the construction site itself, and their experiments spanned generations. A master mason didn't just know how to cut stone, he knew how to read the land itself, listening to its whispers to unlock performance we struggle to replicate with industrial formulas. This deep, place-based intelligence meant that a cathedral in France and a fortress in Syria might use completely different, yet equally brilliant, recipes tailored to their unique climates and available resources. The knowledge was so specialized, so tied to the hands and eyes of the craftsman, that it rarely made it into the books we typically study. It lived in the guild halls, passed from master to apprentice not through lectures but through shared toil. A young learner would spend years mixing mortars, feeling the texture change with the humidity, watching how a test patch cured in the sun versus the shade. The recipes were guarded secrets, often encoded in cryptic symbols or simple rhymes, creating a fragile chain of wisdom. This very intimacy is what made the knowledge so powerful and so tragically easy to break. When guilds dissolved, when construction booms ended, or when new technologies promised faster results, that deep, slow, tactile understanding simply faded from memory. We replaced a conversation with the material with a command, swapping a nuanced partnership for standardized control. To rediscover what they knew, we must learn to see stone not as a dead commodity, but as a participant in the art of building, a partner whose ancient secrets are still waiting in the walls all around us. That intimate, hands-on knowledge produced materials that still defy our expectations. One of its greatest triumphs lies not on land, but beneath the sea. For nearly 2,000 years, the breakwaters of the Roman harbor at Caesarea have rested in the Mediterranean, constantly battered by salt water and waves. Common sense tells us they should have crumbled to dust centuries ago. Instead, something incredible happened. These submerged structures did not just survive, they actually grew stronger over time. This is the phenomenon of Roman maritime concrete, a material so advanced it feels like science fiction from the ancient world. While the Romans perfected it, the mystery of this self-healing stone would captivate builders for 1,000 years to come, setting a standard that medieval masons desperately tried to match. The secret was not magic, but a specific recipe and a patient chemical conversation with the sea. Roman engineers used a volcanic ash called pozzolana, named for the town of Pozzuoli near Mount Vesuvius where it was first quarried. They mixed this fine, reactive powder with lime and a crucial, counterintuitive ingredient, seawater. When modern researchers finally analyzed cores drilled from these ancient harbor walls, they discovered something astonishing. Inside the concrete, a rare crystalline mineral called aluminous tobermorite had formed over centuries. This wasn't a flaw or a simple binder, it was a living part of the material's structure. Think of it like the immune system of a stone. When tiny cracks form from stress, seawater seeps in. Instead of causing corrosion, this water reacts with the remaining pozzolana and lime, triggering the growth of more tobermorite crystals that literally fill the gaps. The material repairs itself. This self-healing property presents a profound challenge to our modern methods. Our contemporary concrete is designed for speed and immense initial strength, but it has a tragic flaw. It's brittle. Under tension, it cracks, and those cracks let in water and salts that corrode the steel reinforcement inside. Our solution is often more concrete, more repair, a constant cycle of maintenance. The Roman material took a different path. It wasn't reinforced with metal. It was designed to be monolithic and to mature slowly, becoming more resilient through a long, slow chemical dance with its environment. It asked for patience but offered permanence. For medieval builders hearing legends of these eternal Roman works, the goal became clear: replicate this performance without the specific volcanic ash of Italy. They scoured their own landscapes for materials that could mimic pozzolana's reactive properties. In some regions, they used crushed brick or pottery. In others, they found certain types of heated clay or even specific sands that could trigger a similar, if less potent, reaction. The quest was to unlock that same principle of long-term strength, to create a mortar that would not just glue stones together, but would fuse with them over decades into a single, indestructible mass. Their efforts, while not always reaching the Roman peak, led to countless local innovations and recipes that gave us the enduring stone skeletons of castles and cathedrals. So the real question becomes, if they could achieve so much through observation and experimentation, what truly changed when we traded their deep material partnership for our standardized industrial control? The absence of iron in these cathedral stones is not a coincidence, but a deliberate choice with profound consequences. Iron is a common element found in many types of limestone, and when exposed to air and water, it oxidizes. This rusting process creates internal stresses, causing the stone to crack, flake, and crumble from within over time. It is a silent, inevitable decay that medieval builders seemed determined to outwit. When you look at the pristine, pale surfaces of a cathedral like Chartres, standing strong after 8 centuries of wind and rain, you are witnessing the result of a masterful geological selection. The quarriers and masons did not simply take any stone from the ground, they became connoisseurs of the earth's layers. They learned through generations of observation which specific strata within a quarry yielded a purer, more homogeneous limestone, one with fewer of these metallic impurities. This was a form of material science written not in books but in the landscape itself. They read the color, the density, even the sound a stone made when struck. A clean, resonant ring might indicate a tight, pure grain, while a dull thud could betray hidden flaws or veins of weaker material. This knowledge was so critical it shaped the entire logistics of construction. The finest, most iron-free stone was often reserved for the most vulnerable and critical structural elements, the slender columns and delicate tracery that bore the greatest loads and faced the most weather. Lesser quality stone from upper or lower layers might be used for foundations or interior walls, where its weaknesses were less dangerous, but the story may go even deeper than simple selection. Some researchers point to evidence that suggests certain stones might have undergone a form of preparation or treatment. One compelling theory involves the practice of seasoning. Freshly quarried limestone is often saturated with natural moisture, what masons called quarry sap. If used immediately, this stone can be weaker and more prone to uneven curing. Historical accounts and site evidence suggest that master builders would often let their best blocks sit exposed to the elements for a year or more, sometimes through an entire cycle of freezing and thawing. This natural weathering process would do two things. First, it would allow the stone to dry and harden uniformly, increasing its strength. Second, and perhaps more importantly, this seasoning would expose any hidden flaws. A block with a concealed vein of iron-rich material or a weak pocket would likely crack or spall during this waiting period. It would fail the test before it ever reached the cathedral wall, being discarded or relegated to a less critical use. This practice turned time into a quality control agent, using nature's own forces to filter out the imperfect material. The result was a curated skeleton of stone, each block chosen not just for its shape, but for its inherent durability. This forgotten art of sourcing and preparation created a resilience that modern restoration teams struggle to match. Today, when a damaged stone on a centuries-old cathedral needs replacing, finding a perfect match is a monumental challenge. Modern quarries focused on volume and speed rarely take the time to identify and isolate these pristine, pure strata with the same meticulous care. We have the technology to analyze a stone's composition down to the molecule, but we have largely lost the patient, hands-on wisdom of knowing which bed of rock will still be singing its song in 1,000 years. So the cathedrals stand not only as monuments to faith, but as silent lessons in longevity, teaching us that true strength often begins with knowing what to leave in the ground. Yet the selection of perfect stone was only one pillar of their mastery. The other lay in the art of transformation, in the very mortar that bound those stones together. Here we enter a more speculative but deeply intriguing territory, the possibility that some of the most precise and enduring stonework of the past was not cut but cast. This is the realm of geopolymer theory, a controversial idea that suggests medieval alchemists and masons might have possessed a lost chemical art for creating artificial stone. Imagine a material that could be poured into intricate molds like a liquid, setting at room temperature into a substance as hard and dense as any quarried block. Proponents of this theory point to puzzling features in certain ancient and medieval structures, blocks that fit together with seams thinner than a blade of grass, stones with compositions that don't quite match any known local quarry, or structures built with a speed and precision that seems almost impossible with traditional methods. The proposed recipe reads like something from an alchemist's manual. It begins with a specific type of clay, rich in a mineral called kaolinite. This clay is then mixed with an alkaline activator, often derived from the ashes of burned plants, which creates a highly caustic solution. Add lime and a carefully chosen aggregate, perhaps crushed stone or sand, and you have a slurry. This mixture doesn't cure like modern cement through a simple drying process. Instead, it undergoes a complex chemical reaction called geopolymerization. The alkaline solution essentially dissolves the silica and alumina in the clay, allowing them to reorganize into a new, three-dimensional network of molecules. This network binds the aggregate together, creating a synthetic stone that is incredibly strong, durable, and over centuries virtually indistinguishable from natural rock. The implications are staggering. It would mean that some of the flawless, seamless joints in European cathedrals or the massive, puzzle-like blocks in certain ancient monuments might not be a testament to superhuman stone-cutting skill alone, but to a sophisticated knowledge of chemistry. The craftsman would have been part mason, part alchemist, transforming common earth into a noble, enduring material through a carefully guarded recipe. This theory remains hotly debated within academic circles. Critics argue that evidence for large-scale geopolymer use in the medieval period is circumstantial, and that traditional quarrying and carving methods, while immensely laborious, were fully capable of the feats we see. Yet the theory persists because it offers a compelling answer to lingering questions. How did builders achieve such perfect fits without modern tools? How could they source such uniform stone for vast projects? The geopolymer idea suggests they didn't need to source it all. They could manufacture it on site, tailoring the material's properties to the exact needs of the arch, the column, or the vault. Whether fully proven or not, this line of inquiry forces us to reconsider the intellectual landscape of the medieval builder. It places them not as mere laborers following templates, but as experimental chemists working within a tradition that blurred the line between craft and natural philosophy. Their workshop was a crucible where earth, fire, and water were coaxed into new forms, all in pursuit of a single goal: to create a material legacy that would whisper its secrets to the future. So if they could indeed cast stone like we cast metal, what other transformative recipes have been lost to time, waiting to be rediscovered in the silent chemistry of ancient walls? While the geopolymer theory remains a captivating mystery, a more tangible and widely used innovation was quietly revolutionizing construction across medieval Europe. This was the mastery of hydraulic lime, a material that defied a fundamental law of building. Ordinary lime mortar needs air to cure, turning soft and useless if submerged. But hydraulic lime performs its magic underwater, setting into a hard, durable stone. For a civilization building bridges over rushing rivers, canals for trade, and fortress foundations in marshy ground, this was nothing short of alchemy made practical. The secret was not in adding a rare volcanic ash, but in a precise dance of heat and chemistry with an ordinary-looking stone. Not all limestone is created equal. The key was finding stone that naturally contained just the right amount of clay impurities. When this specific limestone was baked in a kiln at a perfect, narrow range of temperatures, something extraordinary happened. The heat transformed the clay and lime into new compounds called calcium silicates. These silicates are the heart of the magic. When mixed with water, they undergo a chemical reaction that creates a crystalline network, binding the mortar together even in the complete absence of air. The skill, however, was in the details that were never written down. Identifying the correct source stone was an art passed from master to apprentice. A mason might taste the stone or examine its fracture or burn a small sample to judge the color of the ash. The kiln temperature was another closely guarded secret. Too cool and the silicates would not form. Too hot and the lime would become overburned and sluggish. The ideal was a sweet spot that produced a lively, reactive powder. This knowledge was the lifeblood of the guilds, a form of power as real as any political title. A master who knew how to produce perfect hydraulic lime could guarantee the survival of a critical bridge or the dry foundations of a king's castle, securing wealth and prestige for his entire craft. The resulting mortar was more than just waterproof. It created a bond that was both stronger and more flexible than ordinary lime. It could accommodate subtle shifts in a structure without cracking, allowing a bridge pier to settle into a riverbed or a foundation to move with the damp earth. This flexibility is a quality modern engineers still strive for, as our rigid, high-strength materials often fail under stress because they cannot bend. Today, we face constant battles with water intrusion in our infrastructure. Concrete cracks, steel rusts, and we engage in an endless, expensive cycle of repairs. Medieval builders, with their carefully crafted hydraulic lime, designed for resilience from the very beginning, they understood that a structure must live in partnership with its environment, not simply resist it. Their material was slower to gain strength, but it matured and adapted over decades, growing more integrated with the stone it bound. The next time you see an ancient canal still holding water or a medieval bridge still carrying traffic after 800 years of floods, you are not just looking at old stone. You are seeing the legacy of a profound chemical insight, a recipe born from observing the Earth's own processes and learning to guide them. This raises a humbling question for our age of advanced science. With all our analytical power, have we perhaps forgotten how to listen to what the materials themselves are trying to tell us? The mortar recipes of the past read more like a cookbook for a feast than a builder's manual. Alongside lime and sand, we find records and legends insisting on the addition of egg whites, goat's milk, animal blood, cheese, and even beer. To our modern sensibilities, it sounds like superstition, a desperate attempt to imbue stone with life through symbolic sacrifice. Yet, dismissing these as mere folklore would be a mistake. These organic ingredients were not magic, but they were a form of early material science, a kind of trial-and-error biotechnology that used chemistry they could not yet name to solve problems they understood all too well. Think of a master mason in a damp northern climate, watching his mortar crumble after a harsh winter of freezing and thawing. He might not know about the expansion of water ice within tiny pores, but he knew the result: destructive cracking. Through generations of experimentation, someone discovered that adding beaten egg whites to the mix created a mortar that survived the seasons far better. Today, we understand why. The proteins in egg whites, like albumin, are natural surfactants. When whipped into the wet mortar, they create a stable foam of microscopic air bubbles. These tiny, trapped voids act as pressure relief valves. When water in the mortar freezes and expands, it has somewhere to go, into these bubbles, instead of forcing the material apart from within. It was an ingenious, if accidental, solution to freeze-thaw damage. Other additives served different purposes. Tannins, extracted from oak galls or the bark of certain trees, have natural antimicrobial properties. Mixed into a plaster for a damp castle wall, they could inhibit the growth of mold and mildew, preserving the surface and the health of the inhabitants. Animal blood, rich in proteins, might have acted as an air-entraining agent as well, or perhaps its albumin helped to slow the set of the mortar, giving masons more working time on a large, complex wall. Even beer, with its sugars and yeasts, could have influenced the curing process, potentially creating a slightly more flexible final product. This practice represents a profound shift in how we view these builders. They were not just following rote recipes, they were active experimenters using the entire pantry of their world to tweak and improve their materials. They observed cause and effect, a wall that lasted longer when a certain additive was used, and they passed that observation down. It was chemistry conducted at the scale of the farm and the kitchen, a direct, tangible interaction with organic matter to alter inorganic performance. This stands in stark contrast to our modern chemical admixtures, which are highly engineered, synthetic, and often derived from petrochemicals. We achieve similar or even superior results with precise laboratory control. But their method embodied a different philosophy, one of using locally available, renewable resources to solve hyper-local problems. A recipe in England for a frost-resistant mortar would look different from one in the arid Mediterranean because the available organic materials and the environmental challenges were different. This was sustainability born not from ideology, but from sheer necessity and close observation. So, while we might chuckle at the idea of building a cathedral with cheese, we should also recognize the deep intelligence at work. These builders were listening to the materials, testing nature's own toolkit, and in doing so, they created composite materials that were, in their own way, brilliantly engineered for their time and place. It makes you wonder what other subtle, forgotten interactions between the organic and the mineral are still locked within the stones of the oldest buildings, waiting for us to taste, to test, and to finally understand. But the most dramatic transformation of stone lies not in a careful recipe, but in a blaze of fire. High on the windswept hills of Scotland stand the silent, enigmatic ruins of ancient forts. Their tumbled stone walls hold a secret that has puzzled historians and archaeologists for centuries. In places, the very rocks appear to have melted. The surfaces are glazed with a dark, glassy slag, as if some immense heat had washed over the ramparts, fusing granite blocks together into a single, monstrous mass. This is the phenomenon of vitrified forts, and the mystery of how and why they were created pushes our understanding of ancient material science to its limits. Vitrification is the process of turning a substance into glass. For stone, this requires sustained temperatures far beyond what an ordinary campfire can produce. We are talking about heats exceeding 1,100 degrees Celsius, a forge-like intensity that would make granite flow like thick syrup. The question that hangs over these Scottish hills is a profound one. Was this a catastrophic accident, the result of a fortress being put to the torch by invaders, or was it a deliberate, terrifyingly ambitious construction technique? One theory suggests a desperate final act of defense. Imagine a besieged hill fort, its wooden reinforcements burned away, the enemy at the gates. In a last defiant move, the defenders might have piled immense quantities of timber and brush against the inner faces of their own stone walls and set them ablaze. The goal would not be to destroy the fort, but to transform it. The inferno would, in theory, melt the stone surfaces, which would then cool into an impenetrable, glassy shell. A breached wall could be sealed in a river of molten rock, creating a barrier no battering ram could shatter. It is a scene of apocalyptic ingenuity, turning destruction into a final, hardened shield. Yet other evidence points to a more deliberate, premeditated craft. The vitrification is often found not just in patches, but in extensive, continuous sections of wall, sometimes forming a hard, durable cap. This suggests a controlled process, not a panicked conflagration. Could the builders have mixed specific types of stone, ones with lower melting points, with particular fuels like bone or certain dense woods that burn hotter? Could they have constructed these ramparts with layers of stone and combustible material, then ignited them in a carefully managed burn that literally fused the wall from the inside out? The result would be a rampart of breathtaking strength. A vitrified wall is not just stacked stone, it is a single, monolithic entity. Weathering and erosion attack the joints between stones, but here there are no joints. Wind, rain, and frost would find no purchase. The material would be incredibly resistant to the siege engines of the time, turning glancing blows into shattered fragments. This represents a form of high-temperature stonecraft that seems to border on the mythological. It speaks of a deep, intuitive understanding of pyrotechnics, of how to harness and direct the fury of fire to serve our architectural will. The knowledge required to consistently achieve such temperatures and control the flow of molten stone without collapsing the entire structure is staggering. It hints at a specialized guild of firemasters whose secrets died with them. Today, the vitrified forts stand as somber, beautiful puzzles. The glassy slag, formed over 2 millennia ago, still catches the low Scottish sun, a permanent echo of an impossible heat. They challenge our neat timelines of technological progress. We assume that such control over materials is a modern achievement, yet here is evidence that ancient people might have wielded fire as a building tool, creating a synthetic stone so durable its origins still spark debate. If they could command such elemental forces to fortify a hilltop, what other transformative fires, lit not for destruction but for creation, have been forgotten by history? The true art of building began not at the construction site, but deep within the earth itself. For the medieval mason, the journey to a perfect wall started with a conversation with the quarry, a dialogue that required reading the stone's history written in its very layers. This was a holistic science forgotten today, where choosing the right block was as revered a skill as carving it. It began with the bedrock story. Master quarriers understood bedding planes, the natural horizontal layers in sedimentary stone like limestone and sandstone. They knew that cutting with the grain along these natural planes yielded a block that was stable and resistant to weathering. Cutting against the grain across these layers created a stone prone to splitting and delaminating over centuries, a flaw that could doom an entire column. The timing of the harvest was equally crucial. Stone, like a living thing, had its seasons. Quarrying often took place in the autumn, after the heat of summer had dried the upper layers of the earth but before the deep frosts of winter set in. This timing was deliberate, aimed at managing the stone's natural moisture content, a substance masons called quarry sap. This internal water was not a flaw but a vital characteristic. Fresh from the earth, saturated with this sap, the stone was softer, easier to work and carve with chisels. A mason could shape intricate foliage or delicate tracery with greater precision. But this same moisture posed a long-term danger if not handled with patience. Using a sap-heavy stone immediately in a wall was a recipe for disaster. As it dried unevenly within the thick masonry, internal stresses could build, leading to hidden cracks or spalling where the surface literally peeled away. The solution was a practice that seems almost unimaginable in our age of just-in-time delivery: the art of seasoning. Freshly cut blocks, especially the finest ones destined for critical roles, were not rushed to the site. They were carefully stacked in open-air yards, often for a year or more, sometimes for an entire decade. Exposed to rain, sun, wind, and frost, they underwent a natural curing process. The quarry sap slowly, evenly evaporated. Internal tensions within the crystalline structure relaxed, and importantly, water percolating through the stone could slowly leach out soluble, undesirable salts and minerals, the very impurities that could later cause staining, efflorescence, or weakness. This prolonged, mindful preparation was an investment in centuries. A seasoned block was a stable block. It had already faced nature's tests in the yard and passed. Its dimensions were settled, its hidden weaknesses revealed. When it finally arrived at the cathedral site, the mason knew he was working with a material that had achieved a kind of equilibrium. It would not shift or fail unexpectedly. It was a partner ready for its permanent duty. Contrast this with modern construction. Our magnificent skyscrapers and bridges are built with stone and concrete extracted and processed at an industrial pace. We engineer for immense initial strength, but we often bypass this natural maturation. We compensate with chemical admixtures and dense steel reinforcement, but we lose the inherent, patient stability that comes from allowing the material to find its own balance before asking it to hold up the world. The medieval approach reveals a profound truth about their philosophy. Building was not an act of imposing will upon inert matter, but of guiding a material through its own natural processes to unlock its most enduring potential. They didn't just take stone from the earth, they prepared it for immortality. These master builders did not always have to quarry their stone, sometimes they learned to grow it. In certain landscapes blessed with a unique geology, a natural alchemy was at work, a slow-motion process of petrification that could be guided and harnessed. This is the mystery of the petrifying spring and the stone it creates, tufa. In places like the hills of Italy or the valleys of Central Europe, water emerges from the ground already saturated with a dissolved mineral, calcium carbonate. As this water flows over the surface, it meets the air. A subtle chemical shift occurs, and the mineral begins to crystallize out of the water, much like sugar crystallizing from a saturated syrup. Given centuries, this process can build up natural terraces and cascades of a porous, lightweight rock. But medieval builders saw more than a curiosity. They saw a construction material waiting to be directed. Their innovation was breathtakingly simple and profoundly clever. They would place obstacles in the path of this mineral-rich water. Sometimes it was a framework of woven willow branches, a basket-like form. Other times it was a pile of loose stone or brush. The water would flow over and through this organic matrix, depositing its mineral load layer by microscopic layer, year after year. Over a human lifetime, that woven willow cage would not rot away. Instead, it would become entombed, transformed into a solid mass of stone. The builders were, in effect, three-dimensional printing with nature as their printer head, patiently growing architectural elements in place. The resulting material, tufa, possesses remarkable properties. It is full of voids and bubbles from the original organic material, making it incredibly lightweight, yet the mineral matrix that binds it is strong and durable. This gave builders a stone that was easy to work, provided excellent insulation, and was naturally bonded to its specific site. It was a material born from the landscape, literally. To use it was to engage in a deep partnership with a local biogeochemical cycle, a cycle where water leached minerals from bedrock upstream, carried them to the surface, and with a little human guidance, locked them back into a new, useful form. This practice reveals a mindset that viewed construction as an extension of natural processes, not an interruption. They weren't just extracting resources, they were participating in a geological conversation, nudging a slow natural phenomenon toward a human purpose. The structures built from or with tufa, from ancient Roman aqueducts to medieval church walls, have a unique resilience because the stone formed in its final environment. It is perfectly acclimated to the local humidity and temperature swings. There is no stress from being transported or from seasoning. It cured in situ over decades. This stands in stark contrast to our modern approach, where we manufacture materials in controlled, distant factories and then ship them across continents, often fighting against the very environment we place them in. The petrifying spring method asked for immense patience, a generational perspective few projects afford today. But it offered a reward modern engineering craves, a material with zero embodied energy from transport or high-temperature firing, and a perfect, innate compatibility with its surroundings. It makes you wonder what other gentle, slow-motion processes of the natural world we overlook in our rush for fast, forceful solutions. What if the future of sustainable building lies not in inventing new, complex composites, but in rediscovering how to collaborate with the ancient, patient chemistry already at work beneath our feet? The silent strength of a cathedral lies in its bones, in the precise geometry that channels immense weight into graceful lines. This is where chemistry met mathematics, where the very shape of each stone became a key to unlocking its ultimate potential. Medieval builders understood something fundamental that we often engineer around. Stone is incredibly strong when squeezed, but tragically weak when pulled apart. Think of a block of sandstone. You can pile enormous weight on top of it, and it will hold, but try to bend it or stretch it, and it will snap like a cracker. Their genius was in designing structures that kept almost every stone in a state of pure compression, a constant, gentle squeeze from all sides. They didn't fight the material's nature, they composed a symphony for it. This began with the most basic element, the ashlar block. A perfectly cut rectangular stone seems simple, but its true power is revealed in the joint. The mortar between blocks is not the primary source of strength. It is a bedding, a way to ensure an even distribution of force. The real strength comes from the sheer mass and precise fit, creating a continuous, monolithic wall where gravity flows down through each block in a direct, vertical line. Any deviation, any uneven surface would create a point of tension, a tiny fulcrum where the stone could crack. So the mason's perfect cut was not just for beauty, it was a functional necessity, ensuring that the immense weight of the wall above passed seamlessly into the foundation below. This principle ascended to its most elegant form in the arch. An arch is a miracle of redirected force. Each wedge-shaped stone, called a voussoir, is a carefully calculated puzzle piece. The weight from above pushes down on the crown of the arch. Instead of falling straight down, this force is transformed, channeled outward and downward along the curving line of the arch, transferring the load into the massive piers or walls on either side. Every single voussoir is in compression, each one pushing against its neighbors, locked in a stable, balanced embrace. The keystone at the very top is not holding the arch up. It is the final piece that completes the compression ring, preventing the other stones from sliding inward. It is a perfect, self-contained system of pure squeezing force, but the medieval builders didn't stop there. They took this principle and expanded it into 3 dimensions with the stone vault. A vault is essentially an arch extended along a hallway, a curved stone ceiling. The groin vault, where 2 barrel vaults intersect, represents a leap in optimization. The lines where the vaults meet, called groins, act like stone ribs, creating a skeletal framework that carries the load. The spaces between these ribs, the webbing, can be made thinner and lighter. This is a form of fractal load distribution, where primary lines of force are identified and reinforced, allowing the rest of the structure to be more efficient. The entire ceiling becomes a continuous compression shell, a stone membrane under perfect, even stress. This synergy between form and material represents a forgotten science of structural optimization. Modern engineering often relies on the brute strength of homogeneous materials like steel-reinforced concrete, which can resist both compression and tension. This allows for incredible spans and daring shapes, but it can also lead to a kind of formal laziness. We can make a material do anything, so sometimes we forget to ask what shape would make it perform its very best with the least amount of material. The medieval mason had no such luxury. His material had one great strength and one great weakness, so his entire design philosophy was an exercise in elegance, in guiding forces along natural, compressive paths. He was, in a very real sense, programming strength directly into the geometry. The blueprint was not just a drawing of a building, it was a diagram of flowing force, a map that showed gravity how to travel safely from the spire to the earth. When you stand beneath a Gothic vault, you are not just looking at a roof, you are standing inside a 3-dimensional diagram of a brilliant idea, a fossilized thought about how to make stone sing. But the ultimate testament to this forgotten science loomed over Rome itself, a silent giant that defied every medieval builder who dared to study it. The Pantheon's dome is not merely an ancient wonder, it is a permanent question mark etched in stone and concrete. For over 1,000 years after its completion, its vast, unreinforced span haunted the architects of the medieval world as an unattainable ideal, a ghost of a knowledge they could sense but not fully grasp. While the Romans built it, its shadow stretched across the centuries, challenging every mason and master builder who stood beneath its impossible curvature. The dome's secret was a masterpiece of holistic design, where material science and structural genius were fused into a single, breathtaking object. Its recipe began with the now familiar volcanic pozzolana, but the builders did not stop there. They understood that the weight of the dome itself was its greatest enemy, so they engineered its density layer by layer. At the very top, around the oculus, the concrete mix was lightened with porous, frothy stone like pumice. As the dome descended toward its massive supporting walls, the aggregate within the concrete changed, becoming progressively heavier and denser, from pumice to lighter volcanic rocks, and finally to solid brick and travertine at the base. This was a graduated system, a deliberate manipulation of the material's own weight to perfectly match the structural demands at every point. The dome literally grew stronger and heavier where it needed to be, creating a perfect gradient of compression from crown to foundation. And then there was the geometry. The famous coffered squares that pattern the interior are not merely decorative, they are a brilliant form of subtraction. By carving out these recesses, the builders removed tons of non-essential material from the thickest parts of the dome without sacrificing its structural depth. Each coffer acts like a rib, creating a grid of strength while the voids lighten the overall load. It is optimization carved directly into the fabric of the building. For medieval architects visiting Rome, often as pilgrims, the Pantheon was a shock to the system. They could build pointed arches and soaring vaults, but this was something else entirely. Here was a single, continuous shell of manufactured stone, spanning 142 feet in diameter, with no internal skeleton, no flying buttresses, just pure monolithic form. They would run their hands over the concrete, still smooth after centuries, trying to decipher its composition. They would sketch the coffering, sensing its purpose but perhaps not fully understanding the calculus behind it. The Pantheon stood as a stark reminder of a peak that had been lost, a material science that the so-called Dark Ages had obscured. It was both an inspiration and a frustration. They could emulate its spiritual ambition in their cathedrals, reaching for the heavens with light and height, but they could not replicate its material reality. The specific recipe of Roman concrete and the empirical engineering knowledge behind its graduated construction had faded into legend. The dome became the ultimate case study, a permanent challenge whispering from the past. It asked a question that would take centuries to answer. How do you build not just with stone, but with the very weight of the stone itself as your design parameter? This Roman giant proved that the height of material mastery wasn't about finding one perfect substance, but about orchestrating many different material behaviors into a single, harmonious, and enduring whole. Standing in a courtyard in Delhi is a 7-meter-tall sentinel from another age, a pillar of iron that refuses to rust. For over 1,600 years, through monsoons and scorching heat, the iron pillar from the Gupta era has defied the most fundamental law of metals. Its surface bears a thin, elegant patina, but not a single flake of the destructive rust that consumes modern steel in mere decades. This is not a lucky accident, but a signature of a forgotten metallurgical science, one that was quietly essential to the endurance of countless stone structures across the ancient world. While we marvel at the stones themselves, their longevity often depended on the hidden metal bones that held them together, and the Indian pillar is a masterclass in how to make those bones immortal. The secret was not in a single magical ingredient, but in a sophisticated understanding of the entire process, from ore to finished product. Modern analysis of the pillar reveals a critical clue: an unusually high phosphorus content and a near absence of sulfur and manganese. This was no common iron. The smiths of the Gupta period achieved this through a specific and deliberate smelting technique. They used high phosphorus iron ore and a unique method of forging at a relatively low temperature, which allowed the phosphorus to remain in the metal instead of being driven off. The result was an alloy with remarkable properties. The high phosphorus, combined with the skilled hammering of the forge, promoted the formation of a thin, continuous, and incredibly stable protective layer on the surface. This layer, a compound called mesawite, is a form of iron oxide hydrate, but it is dense, adherent, and non-porous. It acts as a perfect shield. When moisture and oxygen from the air approach, this passive film prevents them from penetrating deeper to attack the pure metal beneath. It is a self-healing barrier, a permanent guardian forged into the very skin of the iron. This technology was not reserved for standalone monuments. Its true power was applied in the joints of temples and fortifications. Across India and in many other ancient cultures, massive stone blocks were often locked together with iron dowels and clamps. In a typical medieval European cathedral, an iron clamp embedded in stone would be a ticking time bomb. As the iron rusts, it expands with tremendous force, up to 7 times its original volume. This expansion creates immense internal pressure, cracking and spalling the surrounding stone from the inside out, a destructive process known as rust jacking. It is a common cause of decay in historical structures, where the very metal meant to strengthen them becomes the agent of their destruction. But with a rust-resistant alloy like that of the Delhi pillar, this danger vanished. An iron dowel forged with this high-phosphorus recipe would not corrode. It would maintain its volume, holding the stones in a firm, unchanging embrace for centuries. The metal became a permanent, passive partner to the stone, rather than its eventual executioner. This highlights a profound and often overlooked truth. The forgotten science of stone materials was never just about the stone. It was a holistic ecosystem of knowledge that included metallurgy, chemistry, and an intuitive grasp of how different materials interact over epic timescales. The Gupta iron masters were not just making a durable metal, they were engineering a component for a larger system of permanence. Their success forces us to reconsider the very definition of corrosion resistance. Today, we often rely on coatings, paints, or stainless steels with expensive chromium additives to protect our metal. Their solution was more elegant and born from a different philosophy. They built the protection directly into the alloy's crystalline structure during its creation, making the shield an innate characteristic, not an applied afterthought. The pillar, then, is more than a curiosity. It is a physical manifesto of a different relationship with material. It whispers that longevity is not about fighting nature's processes with ever stronger barriers, but about understanding those processes so deeply that you can guide them toward a state of peaceful, permanent equilibrium. In a world now seeking sustainable solutions, that whisper from a 1600-year-old forge is growing into a shout we can no longer afford to ignore. The Delhi pillar's silent endurance points to a deeper principle woven into every ancient recipe, a radical form of local intelligence. These forgotten formulas were never meant to be universal. They were hyper-local masterpieces, born from a profound dialogue between the builder and the very ground beneath his feet. There was no global supply chain, no standardized bag of cement arriving from a distant factory. The material palette was the landscape itself, specific clays from a nearby riverbank, regional volcanic ashes from a local eruption, lime burned from stone quarried just over the hill, and organic binders harvested from the surrounding forests and farms. This constraint was not a limitation, it was the source of their genius. It forced an intimate, generational understanding of local geochemistry. A master mason in the dry, sun-baked hills of Spain developed a mortar rich in certain clays that could set quickly and resist relentless heat. That exact recipe, if shipped to the damp, freezing mists of Scotland, would likely have crumbled within a decade, victim to frost and constant moisture. Success demanded a completely different formulation, one that perhaps incorporated crushed seashells for a different chemical reaction, or used a specific peat ash to entrain protective air bubbles. This is environmental intelligence, the ability to read a place's unique personality, its climate, its geology, its seasonal rhythms, and then tailor a material recipe as a perfect response. It was bespoke engineering at the most fundamental level. The builder didn't just construct on the land, he constructed with it, creating a symbiotic relationship where the structure's durability was literally rooted in its location. This stands in stark contrast to our modern paradigm of one-size-fits-all Portland cement. Our globalized material culture prizes uniformity and predictable performance above all else. We have one primary cement recipe that is used from the deserts of Dubai to the rainforests of Brazil, and we then use energy-intensive processes and chemical admixtures to force it to behave in those alien environments. We fight the context instead of collaborating with it. The ancient approach represents a pinnacle of sustainable design, not as a modern ideology, but as a simple necessity. It minimized transportation energy to almost zero, utilized readily available and often renewable resources, and created materials that were inherently acclimated to their environment from the moment they were mixed. The mortar didn't just sit in the wall, it belonged to the wall, and the wall belonged to that specific hillside, that particular river valley. When we look at a medieval village where every building seems to grow organically from the earth, using stone of the same color and texture as the outcrops behind it, we are seeing this intelligence made visible. The entire settlement is a geological echo, a testament to building with, not against, the character of a place. In an age confronting the colossal environmental costs of industrial construction, this forgotten wisdom asks us a difficult but essential question. Have we sacrificed resilience for the sake of convenience, trading a deep, localized partnership with the earth for the brittle efficiency of a global standard? This local intelligence reached its artistic and scientific zenith in the sun-drenched courtyards and shaded halls of the Islamic Golden Age. Here, in the palaces of Andalusia and the mosques of Persia, builders perfected a material that was both a protective shield and a breathtaking canvas, stucco and plaster. In the Alhambra, intricate lattices of carved plaster filter the light into geometric lace, while in Isfahan, entire walls shimmer with floral and calligraphic designs of such depth and precision they seem to defy the very fragility of their medium. This was not mere decoration applied to a surface, it was the surface itself, engineered for both beauty and remarkable endurance. The base of this magic was often gypsum, a soft mineral abundant in arid regions. The first secret was in its transformation through fire, a process called calcination. Raw gypsum was carefully heated to drive off its water content, turning it into a fine, dry powder known as plaster of Paris. But the temperature was everything. Heat it too much and it would become dead burnt, losing its ability to set properly. Heat it just right, and you had a powder that, when mixed with water, would recrystallize into a solid mass, locking into a hard, durable shell. Yet a fast-setting plaster was useless for the artisan tasked with carving the complex, interwoven patterns of arabesque design. His work required time, the ability to shape and refine the material as it slowly hardened. So the second secret was the use of retardants. Builders would add natural substances to the mix, things like animal glue, plant gums, or even certain salts. These acted as chemical moderators, slowing the recrystallization process. This gave the craftsman a crucial window, often several hours, where the plaster remained soft and malleable enough to be carved with knives and fine tools, yet firm enough to hold the sharp edges of his design. The final recipes could produce a finish of astonishing hardness. Some plasters, when fully cured, could be polished to a high sheen, rivaling the smooth, reflective surface of marble. This created a dual-purpose material. On a practical level, it served as a protective skin over softer, more porous building stones, shielding them from wind abrasion and thermal cycling in harsh desert environments. On an artistic level, it became the perfect medium. Unlike stone, which required subtraction, plaster allowed for both additive and subtractive work. It could be built up in layers, molded, and then intricately carved, allowing for a depth and complexity of ornament that would be exponentially more difficult to achieve in solid rock. The result was an architecture where the boundary between structure and art dissolved. The plaster was the wall, and the wall was a masterpiece. Its durability meant that these artistic expressions, these frozen prayers and poems in geometric form, were not ephemeral. They were built to last, preserving not just architectural splendor but cultural memory under the relentless sun. In these silent, stuccoed halls, we see the forgotten science of materials elevated to its highest purpose, not just to endure but to speak, to inspire, and to guard beauty itself across the centuries. A stone wall does not have to be a passive victim of the rain. In the hands of a medieval mason, it could become a living surface, one trained to grow its own armor. This is the subtle art of patination and surface hardening, a proactive craft where the builder didn't just protect the stone, he taught it to protect itself. Far from being simple weathering, many ancient surfaces show signs of an intentional chemical encouragement. The goal was to seal the stone's microscopic pores, those tiny gateways where water, ice, and biological spores could invade and begin their slow work of destruction. One of the most elegant methods involved nothing more than lime and water. A lime wash, a thin slurry of slaked lime, would be brushed or sprayed onto a freshly laid wall. As it dried, it reacted with carbon dioxide in the air, undergoing a process called carbonation. This transformed the surface layer back into a hard, continuous shell of calcium carbonate, the very same mineral that makes up limestone. It was like giving the wall a new, seamless skin, one that was chemically identical to the stone beneath, creating a perfect bond. But the recipes grew more sophisticated. In some traditions, masons applied diluted solutions of tannins from oak galls or even mild acidic substances like soured milk or vinegar. This might seem counterintuitive to put acid on stone. Yet, applied with precise knowledge, these washes could etch the surface just enough to remove loose grains and encourage the formation of new, stable mineral crystals that locked the surface together. Other recipes called for applications of linseed oil or walnut oil, which would penetrate the pores and polymerize, hardening into a flexible, water-repellent barrier that still allowed the stone to breathe. This philosophy represents a fundamental shift in thinking about materials. We today often operate under a paradigm of inevitable decay. We install a product, watch its performance decline, and plan for its eventual replacement. The medieval approach viewed a building as an organism that could be nurtured toward greater resilience over time. The material was designed not just to resist the environment, but to engage with it in a beneficial way. That thin layer of calcium carbonate patina is not a flaw, it is a feature. It improves with age, growing denser and more protective with each passing decade as the carbonation process continues deeper into the surface. It actively repels liquid water while allowing water vapor to pass through, preventing the destructive buildup of moisture behind the surface. This stopped the growth of algae, lichens, and mosses not with toxic biocides, but by creating an inhospitable, dry surface. The entire structure was on a trajectory toward greater stability. This practice reveals a mindset of stewardship that extended far beyond the construction phase. Maintaining a building wasn't just about fixing what broke. It was about periodically applying these knowledge-based treatments, these chemical nourishments, to guide the material along its ideal path of maturation. The mason's relationship with his work was never truly finished. It evolved into a gentle, long-term guardianship. When we look at an ancient stone facade that still appears crisp and defined after 800 winters, we are likely seeing more than just good quarry stone. We are witnessing the legacy of this forgotten science of surface, a science that understood that true endurance isn't about fighting time, but about inviting the stone to join in its own defense. The sea itself became a quarry for those who knew how to ask. In the sun-bleached atolls of the Maldives and along the fortified coasts of the Caribbean, builders faced an environment that devours stone, a constant cycle of salt, wind, and relentless waves. Their ingenious solution was to build with the skeleton of the sea, crafting a material that was not just resistant to the ocean, but a biological cousin to it. This is the mystery of coral stone, a forgotten composite that represents one of history's most elegant examples of a circular economy. They did not simply cut blocks from living reefs, an act that would have been both unsustainable and weak. Instead, they gathered the rubble of dead coral, the broken fragments that washed ashore or were harvested from specific areas. This coarse, porous aggregate was then bound with a remarkable mortar. The binder was lime, but not from a limestone quarry. They burned pieces of coral in kilns, transforming calcium carbonate into quicklime, which was then slaked with water to create a paste. This was coral lime, a binder born from the very substance it was meant to hold together. When mixed, the coral rubble and the coral lime created a monolithic stone. The chemistry here is profound, because both the aggregate and the binder shared an almost identical chemical makeup with the surrounding seawater and the existing marine environment. The finished wall achieved a state of near-perfect harmony. There was no dramatic difference in pH or mineral content between the building block and the spray constantly hitting it. This compatibility neutralized one of the most destructive forces in coastal masonry, salt crystallization. In a conventional sandstone or granite wall, salt water seeps into pores. As the water evaporates, the salt crystallizes. These growing crystals act like microscopic wedges, exerting immense pressure from within, slowly but surely prying the stone apart grain by grain. It is a relentless, unstoppable decay, but in a wall of coral composite, this process is drastically reduced. The material is already saturated with similar salts and minerals. The driving force for destructive crystallization, that stark difference between the stone's interior and the marine environment, simply doesn't exist. The wall sees the sea not as an enemy but as a relative. The result was a fortress that could emerge from the shoreline as if it had grown there, a geological extension of the coast. The old forts of the Maldives, built from this living stone, have withstood centuries of tropical storms and monsoon tides. In the Caribbean, similar structures stand where imported European stone would have crumbled long ago. This practice reflects a deep, sustainable intelligence. It used a local, abundant, and renewable resource, dead coral rubble, in a cycle that had almost no environmental footprint. The energy required was minimal, the transportation distances were short, and the material was perfectly suited to its purpose from the moment it set. They created a closed loop, using the sea's own discarded architecture to build a new one, crafting a shield from the very thing it was meant to guard against. It was a dialogue with the ecosystem, not an imposition upon it. In an age now grappling with rising seas and eroding coastlines, this ancient, quiet collaboration between builder and ocean offers a whisper of a different path, one where resilience is found not in defying nature, but in learning to build with its own enduring logic. The stone itself whispered its secrets to those who knew how to listen. A master mason did not see a block of limestone as a blank slate, but as a living record of immense pressure and ancient seas, its internal story written in subtle lines and hidden whispers of weakness. His greatest skill was not in carving ornate figures, but in the first decisive act, the art of splitting the stone along its own hidden intentions. This was an intuitive science of fracture mechanics, learned not from textbooks but from a lifetime of feeling the material's resistance and surrender. He would run his hands over the rough surface, reading the grain like a map. A tap from his hammer at a precise point, with a specific angle of force, could send a clean fracture racing through the stone, following a plane of weakness laid down millions of years before. This knowledge was everything. To split against the grain across the natural bedding was to invite a hidden flaw, a ticking clock of future failure buried deep within the heart of a cathedral column. So every block was oriented with sacred attention. The natural layers, those ancient sedimentary planes, were always positioned to run horizontally in the wall, perfectly aligned with the direction of the immense compressive force flowing down from the vaults above. This meant the stone was being squeezed along its strongest axis, with its internal laminations acting like the pages of a closed book pressed firmly together. A block placed incorrectly with its layers vertical would be like trying to hold that book open by its covers, the pages ready to delaminate under the weight. This hands-on wisdom was a form of embodied science, a deep catalogue of failure modes held in the muscles and the mind. A mason knew the sound of a good strike, a clean ring, versus the dull thud that warned of a hidden fissure. He knew how a particular type of sandstone would behave under the chisel on a frosty morning versus a humid afternoon. He understood that the quarry sap within a freshly split block made it more pliable, but that this same moisture, if trapped, could freeze and explode the stone from within during its first winter in the wall. Every decision, from the initial split to the final placement, was a calculated move to outwit time and stress. It was a continuous quality control, filtering out weakness at every stage. A stone that split unpredictably at the quarry was discarded. A block that developed a hairline crack during seasoning was set aside for lesser uses. Only the soundest, most trustworthy material ever earned its place in the final, soaring prayer of stone. This relentless curation, this dialogue with fracture, is why these structures still stand. The mason was not just a builder, he was a diagnostician of durability, partnering with the stone's own ancient history to guide it toward a second, immortal life. Even the waste of one craft could become the treasure of another. Deep within the soil of old European towns, archaeologists often find strange, glassy black rocks, the hardened leftovers from centuries of iron smelting. These are slags, the impurities and silica separated from molten metal. To most, they were just industrial refuse, destined to be piled in forgotten heaps. But to the observant medieval builder, that dark, vitreous material held a hidden potential, waiting to be unlocked by a hammer. Some of these slags, particularly those rich in silicates from the smelting process, were not discarded. They were gathered, crushed into a coarse powder or a fine aggregate, and mixed into mortars and plasters. This was not mere frugality, it was a sophisticated form of chemical recycling. When added to a lime mortar, certain slags could behave in a way that mimicked the prized Roman pozzolana. The silicates within the crushed glass could react with the lime and water, slowly forming additional binding compounds that increased the mortar's long-term strength and density. The result was a composite material with intriguing qualities. The glassy, inert nature of the slag aggregate could contribute to a mortar that was more resistant to chemical attack from damp soils or acidic rainwater. It might also create a harder, more wear-resistant surface for floors or protective renders. This practice reveals a mindset that saw no true waste in the material world, only potential in different forms. The metalworker's furnace and the mason's mixing trough were connected in a sustainable loop. The slag, a byproduct of extracting strength from ore, was then used to impart a different kind of strength to stone and mortar. It was a closed-circle economy operating centuries before the term was invented, where the output of one essential industry became the input for another. Today, we are only beginning to rediscover the value in such industrial symbiosis, researching how modern slags from steel production can be used in green concrete. Our medieval predecessors, working on a smaller, more local scale, simply saw the logic in it. They understood that everything drawn from the earth could be returned to it in a new, useful form, and that the most durable buildings might just be those crafted from the overlooked fragments of everyday life. A cathedral did not spring from the ground fully formed. Its true strength was not achieved on the day the last stone was laid, but in the quiet decades that followed, as the very mortar between the stones embarked on a slow, silent journey of transformation. This reveals perhaps the most profound chasm between their building philosophy and our own, the critical distinction between mere drying and true curing. For us, concrete is a race against the clock. We measure its success by how quickly it achieves a high compressive strength, often within 28 days, so that construction can sprint forward. We confuse the hardening of the surface with the completion of the material's inner work. For the medieval mason, this was a fundamental misunderstanding. His lime mortar was not finished when it lost its wet sheen. That was simply the end of the beginning. The magic happened invisibly over years and generations. When slaked lime mortar is placed between stones, it begins a lifelong conversation with the air. This is the process of carbonation. Carbon dioxide from the atmosphere slowly diffuses through the porous mortar, reacting with the calcium hydroxide to form sturdy calcium carbonate crystals. This isn't a superficial crust, it is a gradual conversion from the inside out, a process that can continue for a century or more, steadily increasing the mortar's density and bond. Simultaneously, if pozzolanic materials like crushed brick or volcanic ash were in the mix, a second, even slower reaction was underway. These silicates continued to react with residual lime and moisture, forming additional binding gels that filled the tiniest voids, making the mortar progressively more monolithic and impervious. The structure was literally growing stronger with age, its skeleton fusing into a single, resilient mass. This understanding fundamentally shaped how they built. They constructed in deliberate phases with a patience that feels alien today. A foundation might be laid and then left for a year, or even a generation, to settle and consolidate under its own weight before the walls rose upon it. Towers were often completed by the sons or grandsons of the original master mason, not because of lack of skill, but because the lower sections needed time to mature and gain strength before bearing the colossal load of a spire. They saw the building not as a static product, but as a living entity with a childhood, an adolescence, and a mature adulthood. Its greatest vigor lay ahead of it. This long-term perspective was woven into the fabric of their craft. A contract for a cathedral might span 50 years, acknowledging this necessary timeline of material maturation. The builder knew he would not see his work reach its full potential, and he was at peace with that. His legacy was the potential itself. Contrast this with our modern paradigm. Our economic and logistical models demand speed. A building must be watertight and generating revenue within months. We engineer materials for rapid early strength, but this often comes at the cost of long-term resilience and flexibility. The very haste of our construction can lock in stresses, trap moisture, and create the microfractures that become the pathways for future decay. We trade the deep, enduring cure for the quick, brittle dry. The ancient approach asks us a difficult, reflective question. In our pursuit of building faster, have we inadvertently designed our world to be more temporary? Their stones whisper that true permanence is not a quality you install, but a state you patiently cultivate, one slow, crystalline bond at a time. The Great Pyramid once wore a skin of light. Before wind and time stripped it down to its stepped core, the monument gleamed under the Egyptian sun, encased in tens of thousands of polished white limestone blocks. For medieval travelers and scholars hearing tales of this lost wonder, the casing stones of Chora limestone were not just a facade, they were the ultimate riddle in material perfection. How could blocks so immense be cut so flawlessly, transported so far, and fitted with a seam thinner than a thought? This was a mystery that haunted the medieval imagination, a ghost of a technology that seemed to belong to the gods. The stone itself was a masterpiece of selection. Quarried from the fine-grained beds across the Nile at Chora, this limestone was prized for its purity and homogeneity. It lacked the coarse fossils and erratic veins found in other deposits, offering a blank, uniform canvas that could take a high polish, reflecting the sun with a blinding, almost divine radiance. But the true genius lay in the joint, the surviving casing stones at the pyramid's base, and those found buried around its perimeter, reveal a fit of staggering precision. The mating surfaces were not merely flat, they were perfectly planar, with a microscopic accuracy that allowed them to lock together without any visible mortar. The gap between them is often less than half a millimeter, a space too fine for even a blade to penetrate. This was not just careful work, it was a statement of total control over the material, a defiance of the very idea of weathering at the seams. The logistics behind this feat boggle the mind even today. Each casing block, weighing many tons, had to be cut with this impossible flatness at the quarry, shipped across the Nile, dragged up the growing pyramid ramp, and then set into its final position with hair's breadth accuracy. The process implied a system of measurement, quality control, and skilled labor operating on an industrial scale millennia before the industrial age. It suggests the use of master jigs or surface plates, reference slabs of known flatness against which every block could be checked and corrected. The masons were essentially creating a three-dimensional puzzle of tens of thousands of pieces, where every single interface had to be flawless for the final, seamless geometry to hold. For medieval architects struggling to achieve tight joints in their own cathedrals, the legend of the pyramid's casing was both an inspiration and a profound frustration. It represented a material standard they could envision but not replicate, a lost art of stone fitting that seemed to erase the very concept of erosion at the joints. This points to the casing's ultimate purpose. It was not mere decoration. That smooth, continuous white shell was a monumental raincoat. It protected the softer, more variable core masonry, the large, rougher blocks we see today, from direct exposure to wind, sandstorms, and the rare but destructive desert rains. By shedding water instantly and presenting no cracks or ledges for material to accumulate, the casing would have prevented the capillary action and freeze-thaw cycles that slowly destroy ordinary stonework. It was a sacrificial armor of the highest quality, designed to take the brunt of the elements so the structure within could sleep undisturbed for eternity. The loss of this casing, largely removed over centuries for other building projects, is a stark lesson. It reveals that the longevity of the most ambitious structures often hinges on their outermost skin. Once that superior protective layer was gone, the core became vulnerable, initiating the very process of decay the original builders had so ingeniously designed against. The Great Pyramid, in its rugged, stepped form, is a monument to its own incredible core strength. But in its original, luminous glory, it was a testament to something even more profound, the understanding that true immortality in stone requires a perfect shield, a second skin crafted with a precision that makes the very air between the blocks an enemy of time. This composite intelligence is what truly set their structures apart. A medieval wall was not a single substance, but a carefully orchestrated system. At its heart, a mass of rough rubble and mortar provided bulk and stability at low cost. This core was then sheathed in a protective skin of finely cut ashlar blocks, their tight joints and dense faces deflecting wind and rain. Binding it all together was not a rigid glue, but a flexible lime mortar designed to accommodate subtle shifts without cracking. And at critical points, iron clamps or dowels, forged from alloys resistant to rust, locked the stones in place. Each component had a specific role, and each compensated for the weakness of another. The rubble core was cheap and massive, but vulnerable to erosion, so the ashlar face shielded it. The ashlar was strong in compression but could be brittle, so the flexible mortar allowed it to move as a unit. The iron provided tensile strength where stone was weak, but only because its rust-resistant recipe prevented it from swelling and bursting its stone prison from within. This was not just building, it was a form of material systems engineering forgotten today. They understood that no single substance was perfect. Instead of seeking a mythical, flawless material, they designed with diversity, creating a whole whose resilience was far greater than the sum of its parts. It is a profound lesson from the past. Our modern obsession often seeks the one perfect polymer, the ultimate alloy, the super concrete. Their wisdom suggests a different path, that true durability might lie in the thoughtful, synergistic combination of humble, well-understood materials, each playing to its strengths in a collaborative defense against time. The humid jungles of Southeast Asia hold a material that seems to defy its own nature. In the ancient kingdoms of Cambodia and Sri Lanka, builders mastered a stone that began as soft clay. This is laterite, a deep red, iron-rich earth that undergoes a miraculous transformation when exposed to the one thing abundant in the tropics, air. Its use represents a profound understanding of geochemistry, where construction was not an act of assembly, but of triggering a material's own latent desire to become stone. The process began in the quarry during the wet season. Saturated with monsoon rains, laterite is soft and malleable, almost like a dense, gritty clay. It could be cut from the earth in large, heavy blocks using simple wooden tools. In this soft state, it was surprisingly easy to work. Artisans could carve intricate decorative patterns, door frames, and even foundational sculptures directly into the block before it ever left the ground. This was the window of opportunity, a brief period where the material was as cooperative as wet timber, but the true genius lay in what happened next. These carved, soft blocks were then carefully transported to the temple site. Once positioned in the wall or set as a foundation, they were left to the elements. The tropical sun and the circulating air began a slow, irreversible chemical process. As the block dried, the iron oxides and hydroxides within the clay underwent a dehydration reaction. The moisture that gave the laterite its plasticity evaporated, and the iron particles began to recrystallize, binding the surrounding clay and silt particles together in a rigid, cement-like matrix. The block didn't just dry out, it petrified. Over weeks and months, it hardened from the outside in, turning from a workable clay into a substance as durable as sandstone, resistant to both the relentless humidity and the mechanical erosion of the jungle. This method was a masterstroke of efficiency and environmental harmony. At Angkor Wat and other monumental complexes, laterite often formed the hidden core of structures, the sturdy, reliable foundation upon which more ornate sandstone facades were laid. It was the quiet, resilient skeleton of the empire. Builders were essentially using the sun and the wind as their kiln, allowing nature to complete the final and most critical step of the manufacturing process. They didn't need to burn fuel to fire bricks or quarry distant, hard stone. They simply understood a local material's unique chemical pathway and created the conditions for it to follow that path to strength. This practice reflects a philosophy of profound patience and observation. It required knowing exactly how long to let the blocks season in the quarry, how to handle them without deforming them while soft, and how to orient them in the wall to ensure even curing. It was a dance with humidity and time. The resulting material, while sometimes rough in appearance, possessed a great resistance to the very environment that created it. In a landscape where relentless moisture rots wood and encourages lush vegetation to crack apart ordinary masonry, laterite stood firm. Its iron-rich composition made it inhospitable to the roots of fast-growing jungle plants, helping to preserve the structural integrity of temples even as they were swallowed by the forest. This forgotten science of triggered hardening asks us to reconsider the very definition of a building material. We typically think of materials as having fixed states, but laterite taught that a substance could have multiple lives, a soft phase for shaping and a hard phase for enduring. The builders of Angkor did not just use what the land provided. They understood a hidden potential within the red earth, a secret strength waiting for nothing more than sunlight and air to awaken it. A collapsed arch was not merely a disaster, it was a masterclass in physics written in shattered stone. This vast, intricate science of materials was not handed down from ancient scrolls or divine inspiration. It was painstakingly assembled, fragment by fragment, through a brutal and unforgiving curriculum of failure. For every soaring cathedral that still stands, there were countless walls that leaned, towers that cracked, and mortars that turned to dust within a generation. These were the costly, essential textbooks of the craft. A master mason did not learn his deepest lessons in the quiet of a drafting room, but in the deafening roar of a falling scaffold or the slow, silent creep of a fatal crack across a facade. Each catastrophe was a question posed by nature, demanding an answer. Why did this particular limestone from the North Quarry spoil after 10 winters, while the stone from the southern bed remained sound? Why did a mortar mixed with river sand hold firm in a dry crypt but crumble to nothing in an exposed parapet? The answer was always hidden in the material itself, in the subtle interplay of chemistry, climate, and force that only revealed its secrets under the stress of real use. This process was empirical, iterative, and agonizingly slow. It was a science conducted at full scale, with no laboratory models to soften the consequences. A flawed assumption could mean years of labor lost, fortunes wasted, and sometimes the tragic loss of life. Yet from each failure, a hard-won truth was extracted. A guild might decree that henceforth, no iron clamp should ever be set within a certain type of sandstone, for they had witnessed how its rust could burst the stone like an overripe fruit. Another rule might dictate that foundations must rest through 2 full winters before walls rise upon them, a lesson paid for with the slow, sinking tilt of an ambitious tower. These were not superstitions, they were codified experiences, safety protocols written in the memory of past collapses. This collective intelligence, built over generations, became the true inheritance of the craft. An apprentice learned not just how to cut a joint, but why a joint cut in a certain way had failed a century before his birth. The knowledge was stored in the very practices, in the specific sequence of mixing a mortar, in the seasonal timing of quarrying, in the wary eye cast upon a stone with a particular colored vein. It was a living library of what not to do, and more importantly, a deep, intuitive understanding of why. This stands in stark contrast to much of our modern engineering process, where failure is often designed out through theoretical modeling and safety factors long before a shovel hits the ground. Our lessons are learned more often in simulations than in rubble. While this saves immense cost and prevents tragedy, it can also distance us from the raw, tactile feedback of the material. We may not develop the same gut-level intuition for when a stone is singing true or when a mix feels fatally wrong. The medieval mason's science was born of a direct, often harsh, dialogue with physical reality, a conversation where the material always had the last and most instructive word. Their legacy, then, is more than just a collection of durable recipes. It is a testament to the power of observed truth, purchased at great price and held in trust for the future. It suggests that perhaps the deepest understanding does not come from avoiding failure, but from learning with relentless humility how to listen to its every whispered lesson. The volcanic ash of Italy was a treasure they could not possess, but necessity has always been the true mother of invention. Across the damp, cool plains of northern Europe, far from any rumbling volcano, medieval masons faced a dilemma. They had heard the legends of Roman concrete that grew stronger in water. They understood the principle of pozzolana, but their own landscape offered no such magical dust. Their solution was not to find a substitute, but to invent one from the very ground beneath their feet. In the smoky workshops of potters and the roaring kilns of brickmakers, they discovered a secret. When certain types of clay were baked at just the right temperature, they underwent a transformation. The intense heat drove out water and altered the clay's crystalline structure, leaving behind a material that was brittle, porous, and chemically hungry. This calcined clay, when ground into a fine powder, behaved in a startlingly familiar way. Mixed with lime and water, it began to react, forming the same silicate gels that gave Roman concrete its hydraulic power. They had created an artificial pozzolan. This was no longer about discovering a gift from nature. It was about forcing a humble material to reveal a hidden potential through the precise application of fire. The process required a keen, almost alchemical understanding. Not every clay would work. It had to be rich in specific minerals like kaolinite, and the temperature of the kiln was absolutely critical. Underfired and the clay remained inert, just red dust. Overfired and it vitrified into a useless, glassy slag that would not react at all. The sweet spot was narrow, producing a material that was soft enough to grind, yet chemically altered enough to be eager for a new bond. This knowledge likely emerged from the waste piles of other industries. A brickmaker might have noticed that the rubble from a collapsed section of his kiln, where the fire burned hottest, produced a strange, crumbly material. An observant mason, ever on the lookout for better mortar, might have taken some of this waste, mixed it as an experiment, and witnessed a slower but undeniable set even in a damp cellar. What began as an accident of the kiln became a deliberate craft. In regions like northern France and England, where good building stone was plentiful but volcanic ash was a myth, these artificial pozzolans became a local secret of resilience. They were used in the foundations of monasteries built on marshy ground, in the linings of wells and cisterns that needed to hold water, and in the mortars of river piers for bridges. This represents a monumental cognitive leap in the history of building. It marks the moment when the builder stopped being solely a forager of nature's ready-made miracles and became an active engineer of molecular performance. He was no longer just a user of materials, he was a creator of them. By learning to calcine clay, he gained a measure of control over his environment. He could now produce a key ingredient for durability locally, on demand, tailoring it to the clays of his own region. This shift from discovery to synthesis is the quiet birth of a modern material science mindset, all happening in the soot and heat of a medieval brickyard. It proves that innovation is not always about a brilliant new idea, but sometimes about seeing a profound new possibility in the overlooked scraps of an old, familiar craft. The silent chemistry of ancient walls is now being heard with tools the original builders could never have dreamed of. In laboratories around the world, scientists are performing a kind of high-tech archaeology, not on artifacts, but on the very fabric of old structures themselves. Using electron microscopes that see down to the atomic scale and X-ray diffraction that maps hidden crystalline structures, they are reverse engineering the recipes we lost. The subject of their study is humble, a core sample drilled from a 2,000-year-old Roman breakwater, a tiny fragment of mortar carefully extracted from behind a Gothic capital. These samples are not just dust and stone, they are time capsules containing a complete blueprint for durability, written in a language of minerals and voids. The goal is astonishingly practical, to translate that ancient blueprint into formulas for a new generation of building materials, ones that could heal our crumbling infrastructure without further harming our planet. This quest has turned the narrative of progress on its head. We are now using our most advanced technology not to invent the future, but to reclaim a profound wisdom from the past. The process begins with a paradox of scale. To understand why a Roman harbor wall is still standing, you must look at what it is made of, not as a solid block, but as a dynamic, microscopic ecosystem. Under the intense gaze of a scanning electron microscope, a slice of Roman concrete reveals a breathtaking inner world. It is not a uniform gray mass, but a complex, heterogeneous landscape. Sharp, angular fragments of volcanic ash are locked in a matrix of lime, and everywhere, growing like delicate flowers in a stone garden, are the crystalline formations of aluminous tobermorite. This is the self-healing mineral, and seeing its intricate, interlocking structure explains everything. It shows how the material was designed not for a single moment of strength, but for a continuous, slow-motion chemical conversation that filled its own weaknesses over centuries. Similarly, analysis of medieval mortars often reveals a purposeful imperfection, a scattering of microscopic air bubbles deliberately entrained by organic additives. These voids, which a modern engineer might see as flaws compromising strength, are now understood as brilliant pressure relief valves, the secret to surviving 1,000 freeze-thaw cycles. This nanoscale detective work is decoding the functional intelligence hidden within what we once dismissed as simple, primitive mixes. This is far more than historical curiosity. It is a race against time with immense environmental stakes. Our modern built world rests on a foundation of Portland cement, a material whose production is one of the largest single sources of human-caused carbon dioxide emissions on Earth. The process of making it requires heating limestone to extreme temperatures, a massively energy-intensive operation that releases stored carbon directly into the atmosphere. Furthermore, the concrete it creates, while incredibly strong initially, has a lifespan often measured in decades, not centuries. We are locked in a cycle of building, decaying, and rebuilding, each cycle consuming vast energy and resources. The ancient materials offer a tantalizing alternative. Their recipes frequently used little to no high-temperature processing, or they utilized industrial byproducts like slag. They were often mixed at ambient temperatures and gained strength through slow, low-energy chemical reactions with the environment. In essence, they were low-carbon technologies by necessity, and their legendary durability points to a path out of our disposable construction paradigm. Scientists are not trying to copy these recipes exactly, but to understand the principles behind them, to learn how to design modern concretes that can self-heal microcracks, that incorporate recycled and local materials, and that mature into stronger, more resilient forms over time. So we find ourselves in a poignant and ironic loop. The very industrial mindset that dismissed these old ways as obsolete, that prioritized speed and standardization over longevity and locality, has now created the problems we desperately need to solve: climate change and crumbling infrastructure. And to solve them, we are deploying the ultimate fruits of that industrial age, our particle accelerators and supercomputers, to patiently decipher the quiet, patient wisdom of the pre-industrial world. We are using satellites to study ancient land use patterns that informed quarry selection, and molecular simulators to model the geopolymerization reactions medieval alchemists might have stumbled upon. The quest is to perform a kind of alchemy ourselves, to transmute the data from our electron microscopes into practical, scalable solutions that can build a world meant to last. It is a humbling acknowledgement that the answers to some of our most pressing modern dilemmas may have been resting in plain sight all along, waiting in the stones of a forgotten harbor or the mortar of a silent cathedral, simply asking us to look closely enough to understand their slow, enduring song. That intimate, hands-on dialogue with stone reveals a deeper truth about how they saw the world. For the medieval master builder, the material was never just a resource, it was a participant in the act of creation. Limestone was not an inert commodity to be consumed. It was a substance with a specific temperament, a memory of ancient seas, and a potential for strength that had to be carefully coaxed forth. This philosophical stance, this view of material as a partner, may be the most profound and forgotten science of all. It stands in stark contrast to the industrial worldview that shapes our modern built environment, where material is seen as a standardized passive resource, a blank slate upon which to impose our will. The difference between these two perspectives is not merely semantic, it is a fundamental divide in how we relate to the physical world, and it has tangible consequences for what we build and how long it lasts. The partner mindset began with observation and respect. A mason would spend a lifetime learning to read stone, to understand which bed in the quarry yielded blocks that sang with a clear ring when struck, indicating a tight, durable grain. He learned the seasons of the material, knowing that stone cut in autumn, after the summer heat had drawn out the quarry sap, would cure differently than stone cut in the damp of spring. This was not superstition, it was a recognition that the material had its own processes, its own timeline, and its own inherent qualities that the builder had to work with, not against. The entire craft was an exercise in collaboration. When mixing a mortar, the mason wasn't just combining ingredients according to a fixed formula, he was adjusting in real time. He felt the sand between his fingers, judged the humidity in the air, and tweaked the mix to suit the day and the specific stone he was laying. If a block showed a hidden flaw as it was being shaped, he didn't force it into place. He adapted the design or set it aside for a less critical role. The material had a voice in the process, and a wise builder listened. This respectful partnership naturally led to more careful, more sustainable practices. Because you saw the stone as a partner, you did not waste it. You selected with intention, you seasoned with patience, and you designed shapes that played to the material's natural strength in compression. You sought to create a harmony between the form and the substance, so that the finished building felt like an extension of the landscape, not an imposition upon it. The modern industrial view, born from the Enlightenment and the factory floor, operates on a different principle, one of domination and standardization. In this framework, consistency is king. A bag of Portland cement must perform identically whether it is used in Phoenix or Oslo. A steel I-beam is valued for its predictable yield strength, not for the unique character of its ore. This approach has given us incredible things: the soaring span of a suspension bridge, the impossible height of a skyscraper. It has democratized construction and enabled progress at a breathtaking scale. But it has also created a certain distance, a disconnection. We specify materials by date to sheet, not by touch or taste. We engineer around a material's weaknesses with reinforcements and admixtures, rather than designing to celebrate its inherent strength. The material becomes a servant to the design, forced to comply, often at a high energetic and environmental cost. Perhaps then, the legendary durability of ancient stonework springs from this foundational attitude. The strength wasn't just in the pozzolana or the perfect joint, it was in the relationship. When you approach material as a partner, you invest the time to understand it deeply. You are less likely to commit the hubris of forcing a square peg into a round hole, a mistake that might not reveal itself as a catastrophic collapse, but as a slow, inevitable decay over a century. You build with a humility that acknowledges you are not the sole author of the structure's longevity. You are a facilitator, helping the stone achieve its own most enduring state. This is not a call to abandon modern engineering, but an invitation to reintegrate a lost wisdom. What if our most sustainable future lies not in inventing ever more complex materials to dominate nature, but in recovering the art of collaboration? What if the next leap in durability comes from algorithms that don't just calculate load, but can model the long-term chemical conversations between a local clay, a recycled aggregate, and the specific climate of a building site, designing for a partnership that matures over 100 years? The stones of the past whisper that the most resilient structures are born from a conversation, not a command. They ask us to consider whether true strength is something you extract or something you cultivate together. This forgotten tapestry of ingenuity weaves a single, undeniable truth. The strength of these ancient materials was never a simple accident of chemistry or a lucky find in a quarry. It was the direct result of a profound and patient way of thinking, a science that was empirical, hands-on, and deeply woven into the culture and landscape of its time. These builders conducted experiments that spanned generations, their laboratories the construction sites themselves, and their data written in the silent endurance of walls that refused to fall. They measured success not in quarterly reports or 28-day strength tests, but in the quiet passage of centuries. Durability was a long conversation, and they were masters of listening to its slow, steady rhythm. This perspective represents a radical shift from our own. We live in an age of acceleration, where speed and immediate performance are often the highest virtues. We engineer materials to be installed quickly and to bear immense loads almost instantly, but we seldom ask how they will behave in 100 years, let alone 1,000. The old masters asked that question with every block they laid, every mortar they mixed. Theirs was a science of deep time, an understanding that true resilience is not a quality you bolt on, but a potential you cultivate through patience and profound respect for the material's own nature. As we now confront the monumental challenges of our own era, from the carbon footprint of our industries to the alarming decay of our modern infrastructure, these ancient lessons cease to be mere historical curiosities. They become urgent, living wisdom. They challenge the very core of our material philosophy. We are experts at creating strength, but are we wise enough to create longevity? We can build taller and faster than ever before, but can we build something that our great-great-grandchildren will not need to tear down and rebuild? The stones of the past offer a different blueprint. They point toward a future where materials are not standardized global commodities, but are intelligently tailored to their local environment, using local resources in low-energy cycles. They suggest that durability can be designed into the molecular conversation of a material, creating structures that maintain themselves, that adapt, and that grow stronger in partnership with the world around them. This is not a call to abandon steel and glass, but an invitation to expand our imagination. What if our bridges could heal their own micro-cracks like Roman concrete? What if our cities could be built from composites that actively absorb carbon as they cure? What if we could recover the art of listening to a place, of building with it, rather than simply building upon it? The answers are not all in the future. Many of them are waiting in the past, encoded in the quiet chemistry of a medieval mortar or the flawless joint of a pyramid's casing stone. Our journey ends not with a conclusion but with an opening. The most enduring legacy of these forgotten sciences may not be the stones they left behind, but the question they pose to us now. In our pursuit of progress, have we forgotten how to build for forever? The walls of history are still standing, and they are waiting for us to learn their language once more. The quiet endurance of these stones is a question posed directly to us. If this journey into a forgotten material science has sparked your curiosity, then a much wider world of lost knowledge awaits. History is not a single story, but a vast library of unread manuscripts, each holding a different kind of wisdom. Perhaps you have stood before an ancient structure yourself, feeling the impossible precision of its joints or marveling at its defiance of the elements. What unexplained feat of building have you witnessed? Which modern material mystery, from the rust-resistant iron of Delhi to the self-healing potential of Roman concrete, captivates your imagination the most? The conversation does not end here. Share your thoughts and discoveries in the comments below, because every viewer's insight adds another piece to the puzzle. For more deep dives into the hidden sciences and silent revolutions of the past, be sure to subscribe and tap the notification bell. Together, we can continue unraveling the grand mysteries of our world, one forgotten recipe, one enduring stone at a time. Let this exploration be a reminder that progress is not always a straight line forward. Sometimes, the most illuminating path to a better future is found by looking back with humility and wonder at the profound ingenuity already embedded in the